Having established this waveform, we can then proceed to discuss the behavior of contact in two different directions. One is along the normal direction and the other one is along the tangential direction. So taking this problem for instance, we have two bodies coming into contact. Body 1 is called the contactor and body 2 is called the target. And basically x1, which is a point on the contactor, is going to search the corresponding point on the target, which is the closest to x1. And that we need to use a distance function. So this distance measures the basically the L2 norm between 2 points. So the x would belongs to gamma 2 and x1 belongs to gamma 1. So x2 would be the point which minimizes this distance. Once we find x2, we can then define two directions. So we can define the normal and tangential direction, and with these directions defined, we can then decompose our contact pressure into the normal and tangential components. And then we can define a gap function, which gives us the normal component of the distance vector between x1 and x2. So with this gap function, we can then proceed to find gamma c, which is the area of contact. So basically, whenever this gap function becomes 0, then we know that there's a contact happening. Mathematically, this is easy to write, but numerically, this is very complex to implement. So this gap function, here, we can see that it is a function of x, and x1 and x2, they are functions of displacement field. So small x equals to capital X plus our displacement. Hence, the gap function itself is a function of displacement. And since we use gap function to find our area of contact gamma c will also be a function of displacement. And there is a well-known condition between the gap and our normal pressure, Tn, which is the so-called Coulomb-Tuck condition. Basically, it says that the product of G and Tn, they must be 0, always. And G is a gap is always larger or equal to 0, and Tn here is the pressure applied on the top surface, and we are taking the positive direction n in this in the upper direction. So Tn is always greater or equal to 0. And graphically, we can represent this condition along the space defined by G and Tn by two straight lines. However, we have a problem. We cannot define exactly the value of Tn when G equals to 0, which means that when the two bodies are in contact, we don't know exactly the contact pressure. The only thing we know is that now they are exerting pressure onto each other and they are in contact, but as in how much pressure is exerted, we don't know. There are two ways to solve this situation, as I mentioned before. One is to associate this unknown Tn with the existing unknowns, like our u solution variable. The other way is to augment our system equation by a constraint equation, so that we keep Tn as an unknown together with u, but now we have one more equation to solve. Along the tangential direction, things are more complicated because there could be sliding and friction. And for this lecture, we assume a simple friction law, which is Coulomb's friction. Basically, we define a certain frictional resistance, which is proportional to our normal contact pressure, Tn, and we define a non-dimensional parameter tau, which is the ratio between Ts and this mu times Tn, our frictional resistance. When tau is between -1 to 1, which means that this frictional resistance is not exceeded, then we have a so-called stick condition, which means that the two surfaces, they stick onto each other without sliding. And when this absolute value of tau equals to 1, we then have this slip condition, which means that there will be sliding. And together we have a friction, and since tau equals to 1, the amplitude of frictional traction would be mu times Tn. We can define a similar gap function but along the tangential direction, and this time it will be equals to u1 minus u2 dot product with the normal vector along the tangential direction, which is s. And from Coulomb's law, we know that the direction of sliding is the direction of applied tangential traction, and this can be mathematically expressed by this equation. So similarly, on a plot, we can write this condition. We can write the stick and steep condition as 3 straight lines. When tau is between -1 to 1, we have a stick condition, which means that our sliding velocity is 0, so no sliding, but we don't know the values of Ts, which means that we don't know the value of tau. When tau becomes -1 or 1, we have sliding, and so the velocity could take any value when tau equals to +1 or -1. Again, we have 2 ways to solve this problem, because now we have additional unknown Ts. Either we associate Ts with the existing unknown, our displacement solution U, or we add a constraint equation to augment our system equation, so that we have 2 unknowns with 2 equations.